Okay. Okay, seems like a lot of us are here already. That's good. Let's get started. Let me see. No, wait. Just draw some more. Okay. Okay, so we are looking at solutions in reactions in aqueous solutions or solutions in general. So we're going to continue with that. This one moved. I don't know why it moved. Okay, there we go. That's our first one. Okay. So solutions. Okay, so as you know, solutions are any combination of two or more things that are usually done in a medium of whatever state, it doesn't matter, but you may have gaseous ones, you may have liquid ones, and you may have solid ones, or liquid and solid, liquid and gas, you know, all of the combinations. This is what we're going to cover. We're going to look at pressure and solubility, Henry's law, solution concentration, of which we've already covered molarity and molality, which are in dilutions, these three. But we are going to cover the rest of it then. All right, so basically, all it is a homogeneous mixture that both contain a solute and solvent. And like I said, the solvent is usually the one that is in greater proportion, and it's what the thing is dissolved in, which is the solute. And any substance that dissolves in a solvent is the solute. Now, something that is not dissolved is said to be insoluble if it is not a liquid. Now, if you have two liquids that are not soluble into each other, like oil and water, for example, they're known as immiscible. And if they do, like alcohol and water, would be miscible. So the words change from soluble to miscible. And then the solutions, they form because of the attractive forces between the solute and the solvent. So the main thing is that you have charges that on both, hopefully. And if you don't have charges, then it still works, but on both of them. All right, so this is how the solvation process happens. The solvent particles will surround the solute to form a solution. And if it's water, is known as hydration. Okay, so once again, remember that polar substances dissolve in polar solvents, and non-polar dissolves in non-polar. So basically, like dissolves like. If you have an energy of change that occurs during the formation of a solution, that is known as the heat of solution, and we will be looking at that too. There are three ways to increase the rate at which a solute dissolves, or the solvation process. That's agitation. So basically you can stir, you can shake, you can do whatever. You can increase the surface area of the solute by making things smaller. And you can increase the temperature. A lot of the times temperature increases works, but not with everything. So we will look at a graph where you can kind of tell that increasing the temperature actually was detrimental to the solution. Now, solubility is known as the maximum amount of solute in a given amount of solvent that will dissolve. And it has to be at a certain temperature and pressure. And it is usually expressed in grams of solute per grams of solvent. And there are 3 types of solutions based on the amount of solute it contains. They are saturated, unsaturated, and supersaturated. And saturated contains the perfect amount, the maximum amount of solute at a given temperature and pressure. Unsaturated contains less the amount of solute than it could take, and supersaturated contains more. So in order to make an unsaturated solution saturated, you add more solute. If you want to make a saturated solution unsaturated, you increase the temperature or the pressure, depending on if it's a gas or not. And if it's supersaturated, you can also increase the temperature to make it saturated. All right, anyway, so let's keep going. For the rest of this, we are going to, as a matter of fact, we have the same chart where we are going to ask you some questions. And right here, it's all about interpretation of the chart. So if you want to determine the approximate solubility of potassium chloride at 20 Celsius. So you look for the temperature, you look for the KCl, and the approximate solubility would be less than 35, but more than 30. So somewhere around 33, maybe, something like that. How many grams of KCl will dissolve in 300 grams of water at 20 Celsius? Okay, so let's look at KCl. And we already, wrong way. There we go. We already said that we had about 33 grams, right? So you locate the curve and you do that, right? So then at 20 Celsius, the solubility is per 100 grams, but they're asking you for 300, right? So for every 100 grams, you have 33 grams of water dissolving. Therefore, in 300 grams, you would get 99. That makes sense, right? So according to the graph, the solubility of potassium chloride at 40 degrees is exactly 40. You see that how it hits that, right? All right. And per 100 kilograms. So how much KCl will dissolve in 300 kilograms of water at that temperature? Well, if normally it's 40 times 3 is 120, right? All right, the amount of additional potassium chloride, that's a typo there, that dissolves at the higher amount, at the higher temperature between the two amounts. Okay, so if you are looking at them, you have 99 on one and 120 in the other, right? So when you subtract, that would be 21 grams by increasing the temperature from 20 to 40, okay? So that's how you would read this kind of graph. You have a problem in your next assignment that will do this same exact thing. All right, so there's some of them, and these are the practice problems right there. And they are the same ones in your questions at the beginning, right? So if you are going to look at those, what you need to do is look at your graph, like I said, like I showed you, at the temperature and the curve that corresponds. All right, so that's that. Next. All right, the solubility of a gas will increase as its external pressure also increases. That is Henry's law. So solution 1 over pressure 1 is equal to solution 2 over pressure 2. So at a given temperature, solubility of a gas in a liquid is directly proportional to the pressure that is above the liquid, okay? So in this case, here's an example of Henry's law. If 0.24 grams of gas dissolves in 1 liter of water at 1.5 atmospheres, how much of the gas will dissolve if the pressure is raised to 6? So if you are applying this law, S1 would be this grams per liter, right? So 0.24 grams in a liter of water at 1 atm, that's the pressure. How much will it dissolve? So this is S1 and P1. And then you have to solve for S2, right? So what you do is right here. See, I always like to take like an inventory of my data that they gave me. And then I use the formula and solve for it. And once I did it, I got 0.96. All right. Here's some practice problems for you. And these are also your problems in your assignment. So you can do those. And you can try them right now if you want. You will have them for your assignment if you do them now. And if you don't do them now, then you still have them for your assignment. So either way, you have to do them. So try doing those. Applying that law, S1 over P1 equals S2 over P2. Paper so I can go along with me. Better pen than this one. Okay. So we need this pressure too. All right. So it's S2P1 over S1. Okay. All right. So did you guys get it yet? And this 266 is enough, so 94. Here's is what I got. Let me see if that's acceptable. This is think that's right. Yep. All right, that's one. What did you guys get on the problem one? Did you do it yet? Oh, somebody chatted. Yep, that is what I got. Correct. All right, next one. Oops, sorry. I did not mean to do that. Next one is another one to do. And like I said, this is the same set of problems that I have in your sheet that is on Canvas. So if you're doing them now and you get them right, then you have the answer already, and you're going to need to show your work. So don't just put the answer. That's the main thing. I want you to show your work because I want to know that you know what you're doing. Okay, so two again. Okay, what is the second one? Don't forget the units too. Very important to have units on your answers. All right, so that's those. That's Henry's law. That's just two practice problems, just so that make sure that you know what you're doing with that. Right, the next thing that we're going to look at is percent solution concentration by percent by mass. So basically the way this works is you measure the amount of solute dissolved in a given amount of solution. So amount by amounts, we mean grams or kilograms or whatever it might be, that is mass, right? Because this is by mass. All right, so the mass of the solute divided by the mass of the solution times 100. Okay, so in order to get, so mass to mass, basically that's what that's called, ml. Here's an example. Okay, you notice he says the percent by mass of potassium nitrate made by mixing 5.4 grams over, you notice it says percent mass of the solution. So that means that you are going to add the two top and bottom. So it's going to be 5.4 divided by the addition of 5.4 and 260. And then multiply it times 100. And that gives you your percent, which is 2.03 in my case, but we only had two sig figs in this one, so it's 2.0 by mass. Now, percent by volume is the same thing, except it's done by volume. And the volumes have, the one thing that you have to pay attention is that the volumes and the mass have to be in the same units. So if it had said divided in this much kilograms of water, you notice it says here it's diluted into milliliters of water, but water is a 1 gram per milliliter density. So you're going to need the density if you're given milliliters to change it if it's not water. Okay, So the volume for the first one, the volume of the solute in this case, and the volume of the solution, again, and then you're going to divide it by, by that, and then times 100. So once again, volume of the solute, in this case, it says 100 milliliter solution. So that's the bottom, right? Mixed by mixing 50 milliliters of water with acetone, so 50. So obviously it's going to be 50 divided by 100 times 100 is going to be equal to 50%. Wait, and this is volume to volume, so V to V. So when you write your answers, it'll be percent by volume. You can write it like that, or you can say percent VV, V over V, which is volume over volume. When M over M on the top one, mass over mass. You can do either one. All right. And yes, always watch your sig figs. In this case, we only had one, right? So one is okay here. All right. Now, there's some practice problems. And these practice problems you are going to do also again in your assignment, or you can do one or two of them now and see if you're getting them right. Once you do that, then you will get it. All right. Sodium carbonate. Okay, this is miswritten because sodium is 1 and carbonate is 2, so that should be Na2CO3. I don't know if it matters right now, but it should be Na2CO3. Just so you know, I just noticed it. I have a typo on there. And you normally, I like to have them fixed because if you need it, you don't want to start with the wrong numbers. So I'm going to fix it right now. And put that as little. There we go. All right, that should do it. So enter. And let's keep going. There you go. Sodium carbonate, not calcium. If it was calcium carbonate, then that would be CaCO3, but it's not. All right, so it's 0.497 grams of the solvent in 43 grams of solution. 58.3 grams, oh Lord, of solution. So you're dividing those two, right? And you tell me what you get. Don't forget the sig figs, because I'll be grading on sig figs too. Just want to try one or two of these just to make sure you can do them. Don't do the number one because it's too easy. Do the other ones. Where it's giving you the percentage, and then you have to calculate something else. So Mhm. All right, here we go. Somebody answered one. All right, you got no. That number one, did you multiply by 100? Something's off. I don't know what. Try it again. It's off by a factor of 10, so we need to redo that one. Okay. Yes, that's better. Correct. Oops, sorry, did not mean to do that again. Every time I click on this thing to get it all away, it clicks my screen too. Okay. Right, 626.5. Oops. Must have done something weird. Okay. Yeah. Okay. All right. Here we go. Yep, that is correct. And if you do number 3 with it, it's easy. You don't have to really do much more. Oh, the only thing is you're off by a factor of 10 again for some reason. No, no, you're not. I think maybe I mistyped it. Let me look at that. If I mistyped it, I might have mistyped it. That happens sometimes. Let's see. Sorry, man. Yeah, it's 1.47, not 14.7. Aha, I knew it. There's something weird on that one. I mistyped it, but the answer that you got is correct. And the answer that I got was correct. And I was like, why on earth is it off? And that's because it's 1.47%. Okay. All right, so you've gotten enough time to do 2 problems, and let's move on. All right, so far we've done all of these. Now we have the next part, which is molarity, and we've already done the molarity ones. Okay, so we have this example. So those of you who weren't here, we can go over this. Molarity is the moles of solute per liter of solution. And you got to have them in these particular units. And if it's not in this unit, you need to convert. Like right here, what is the molarity of an aqueous solution that contains 14.2 grams of sodium chloride dissolved in 2,364 milliliters. So that would be 2.364 liters, right? So you need to make sure you change that before you do the math, because you're going to get a huge amount if you don't. All right, so your answer, first of all, you need to change that to moles. You notice that it says 14.2 grams of sodium chloride. So that's your first thing, is you turn that to moles. How do you do that? Well, you use molar mass. That's why we did mole conversions last class. So 1 mole of sodium chloride is equal to 22.99 plus 35.45. What is that? That is equal to 58.54 grams. 44, sorry, grams. Okay, so that's done here. See that? And that gives you, the answer is going to be 14.2 divided by 58.44. Or 58.5 according to that, but that's all right. And I get 0.24243 moles. Okay, so that's what I get. Here they get 43, yeah, 243, same thing. So whether it's 4 or 5, it's good, but we still only have 3 sig figs because of the 14.2 grams. Once we divide that over the liters, right? Over the liters, which is 2.364 liters, because it's got to be over liters, then you get the molarity of this solution is going to be 0.103 molar. Okay, and that's how you do that. And remember, to find the number of moles, you have to do that. Okay, so this is how many grams of sodium chloride are contained in 1 liter of the solution. Well, you know the molarity. Since you know the molarity is 0.103, and you are going to say that molarity is equal to moles per liter, right? So we know that this is 1 liter, so all you have to do is multiply 0.103, right, times 1 liter, and that gives you how many moles there are. So there are 0.103 moles of sodium chloride, but now you need to know how much that is in grams. So 1 mole of that is equal to 53 58.44, which is what I get. It says gram, it doesn't matter. So you're multiplying 0.103 times 58.44. And that's going to give you 6.03 grams of sodium chloride in 1 liter. See? All right, so that's how you do molarity. Now let's look at the next thing. You have some practice problems. These are the same ones in your homework. So you can do these. We've already done these. Well, we haven't done them, but we already have them posted. So you do those. And if you need help again, just go back to this PowerPoint and you'll see it. Now, the next thing is diluting molar solutions. That's dilutions or solution, dissolving, dissolving, not dissolving, but diluting. All right, so when you're diluting, you have to use this formula. The molarity of the solution 1 times the volume of solution 1 is equal to the molarity of solution 2 times the volume of solution 2. And so basically the first thing is the initial volume and molarity, and the second is the resulting as you're diluting. So it says here, what volume in milliliters of a 1.15 molar stock solution of potassium nitrate is needed to make 0.75 liters of 0.78 molar potassium nitrate. Okay, so you need to do your equation and solve it for volume 1, which is what they're asking, and do your multiplication, divide, and you get your answer, which is volume is equal to 377 liters. And if you want to convert that to milliliters, which is what they asked, it's 377 milliliters. And there you are. That is how you do the dilutions. And we have some problems here for you to do. And they're also already posted, so we're not going to go through these. And the next one is molality. We do have molality. Now those are the practice problems. This moved over. This slide moved over. Hold on, let me move it back where it needs to be. I don't know why it did that, but it did. Okay, solubility, practice problems. Okay, these are the ones that we're talking about. And we need to move that one over. Yeah, the molality problem. Are these molality? No, molarity. Okay, so that's fine. So it's these. No, these are the ones that need to move. Yeah, I need to move this one above that one. Come on, move. It's not letting. Yeah, there it goes. There we go. All right, so now we got molality, which is what we need. Okay, perfect. It's in the right order now. For some reason, it got out of order. Probably when I was scooting it up. All right, molality is the number of moles of solute per kilogram of solvent. So in this case, molality, which is lower capital M, right, or lower letter M, I'm sorry. The other one was capital M, that's what I was thinking, and this is lowercase m. So moles of solute over kilograms of solvent, and it has to be in those units, so make sure that you change that to kilograms. And first, this needs to be changed to moles, which is what we're doing here. 16 grams of potassium chloride. For every mole of potassium chloride, we have 74.6 grams. How do you do that? You do the molar mass. You take the mass of the potassium that is on your periodic table, which is 39 point something, and your mass of chlorine, which is 35.45. Add them together and you get this number. And then you're dividing that by that. the number they gave you over the number that you just got for the molar mass, and that is going to give you the amount of moles. Once you have the moles, then you need to change your grams to kilograms. So we did that. And then now you can divide the two and get your answer. And remember, sig figs are 3, so we need 3. And that's it. And you have a couple of problems, which is, they're in your post-it already. And then now we have this one. This one we didn't cover. So mole fraction. This is the one that always people get confused on. All right, so remember the mole fraction is the solvent is A and the solute is B, okay? So if you think about it, you could say, do you remember the B because it's the base of the solution? The base of the solution is what you diluted in, right? And the A for adding, you add it to the solvent. So see, it's backwards. And that's where it gets confusing. So if you remember it's backwards that way, then maybe it'll help. Because solvent is not what you add, it's actually what's there. And B and the solute is what you actually already add to the solution or to the solvent and make the solution. All right, so find the mole fraction of the solvent and solute in a solution containing 215 grams of water and 0.44 grams of sodium hydroxide. So the very first thing to do is number moles of both. So you need to do the N of water, which is the number of moles of water. And water happens to be the solvent, so Na, right? This would be Na. Is equal to 215, which is what they have, divided by 18.02, which is the mass, the molar mass of water, gives you 11.9 moles. Then you do then the moles of the sodium hydroxide, which the molar mass is 40. And you're dividing 44 into 40, and you get 1.1. Now that you have Na and Nb, right? Then you're going to look at the values into the equation. So you've got Xa, so the mole, a mole fraction of A, which A is the water, right, is equal to the mole of A over the moles of A plus B. So right there, and it gives you 0.915. And this has no unit because they're both moles. And then the molar fraction for B, or the solute, is going to be NB over Na plus NB. So the only thing that changes is the Na and the NB over the other, right? And then that's going to give you 1.1 moles, which is what we figured, divided by the 11 plus, same thing as the other one. And it gives you 0.846. So obviously, the amount of moles that we have is going to be 1, right? So if you actually added those two moles fractions, it should equal to 1. So that's part of what some of the problems are going to be like. All right, so we got 0.915 plus 0.0846. That's going to be equal to 0.999996. So yes, definitely 1, right? All right, so let's keep going and look at a problem. Okay, so just do A, and if you can do A, you can do any of them. So try to do A and see if you can get it. You can go back and look at the formula if you need to. So first you have to, of course, figure out how many moles that is. And then is equal to ethanol. Oops, sorry. This is alcohol is 148 grams. All right. Okay. Okay. Next thing. Okay. Anybody have it yet? You can do one, like I said, you can do the rest. So that's mole fractions. So problem one, I said that's A. Sorry, A. Did you guys get that one yet? That's a lot of calculations just to get two little numbers, but that's how it works. Oops, sorry. Okay. Remember, they should add up to 1 if you did it right. Or close to 1, very close to 1. All right, here we go. We got one answer. Ooh, I got big difference from you. I got 0.841 and 0.159. Maybe your numbers, when you do your molar mass, don't just do 18. It needs to be 18.02. And the other one was 50.08. So you gotta go at least to 2 sig figs with those. I mean, to 2 decimals. That makes it a little bit more clear. But once you did this, of course, you got the right answer, right? Just the bottom and the top. My top is my A, the bottom or the, you know, the XA for me was 0.841. And remember, yeah, the sig figs is good. That's what I got. All right, well, that's good. Now that you've done it, let's keep going on the next one. And normality. Oh, Lord. Yes, as if molarity and molality wasn't enough. Now we have normality and formality. Okay, so what is the difference? Okay, so the normality of a solution is the gram equivalent weight of a solute per liter of solution. So what is the gram equivalent weight? Okay, gram equivalent weight is basically it's the reactive capacity, which, how do you know that? Well, it just depends. The normality is actually the concentration unit that is reaction dependent. So to do that, 1 molar sulfuric acid is 2N. Why? Because you have 2 H's. So it provides 2 moles of hydrogen ions. So basically, whatever molarity you would get, you would double it for normality. Okay. Okay, so here's another example. Hydrochloric acid. See, that's a 1 normal because only 1 hydrogen, right? Only 1 H. And a normal is a 1 gram equivalent of solvent per liter of solution. So hydrochloric acid is strong and it dissociates completely in water. It would only give you a 1 H for either one. Same here. For it would be a 2 normal for a concentration of hydrogen, but a 1 normal for the sulfate because you only have 1 sulfate. So that's kind of how it works. So normality is, like I said, we've pretty much covered it already, but it is like molarity, right? But with the reaction dependent. All right, and then formality. Formality, once again. All right, so how do we do that? Sometimes we do use the term formality instead of molarity because formality takes into account that when electrolytes dissolve or ionize and the ions are not the same as the compound. So formality is based on the formula weight. And that is the sum of the atomic weights of the molecules in the solution. So if you made a 1 molar solution of sodium chloride, you said, are there any sodium chloride molecules in the solution? The answer is no. Why not? Because we have 1 mole of sodiums and 1 mole of chlorine, but no NaCl anymore. So technically, we have positive or negative, right? And we have 0 moles of NaCl. So we use formality that once the solute in the solution has dissolved, then you have this concentration of whatever it is. Okay, so very few people take the time to calculate the true molar concentration of all of the ions. That's why the formality was born. Okay, so over here, for example, weak acid is only partially ionized. So even if you start making this solution by putting 1 mole of hydrogen fluoride in 1 liter, or what? The ionization is complete, but now you will have less than 1 molar hydrogen fluoride and something of just fluoride. Why? Because when it, like it says, since it's a weak acid, it reacts back and it forms the hydrogen fluoride again, or the hydrofluoric acid again. And so it keeps going backwards and forward. So it goes HF, positive H, negative F. So you have that concentration, but you also have the HF concentration because it does not completely ionize. So anything that completely ionizes, yes, you would have a whole formal, but you know, we just keep going with that. And then you have your colligative properties. Colligative properties are very important because this is why when you see icing on the road, people put salt on it. Why is that? Because the ice lowers, it's called freezing point depression. It lowers the freezing point of water to the point where it won't freeze in really cold temperatures. So it is right here, and there is right here, let's see, there it is, delta TB. So it is the solution and the boiling point. So the TB is the delta T of the boiling point, elevation for whatever substance you have. So for example, in delta TF is KF times M, which is once again the molality. You know, this is molality, not molarity, of the solution. Okay, so what you do is you look at, and K is a freezing point depression constant. So how do you find that? Well, there are charts to look for. So let's look at that. Here's an example. All right, so you have what are the boiling and freezing points of a 7.75 molal aqueous solution of potassium bromide. And you notice it says the electrolyte, potassium bromide. Okay, so the effective solute particle concentration, each formula unit of KBr dissociates into 2 ions. So given the molality, it must be doubled, right? Does that make sense? Because you got to double it because you have 2 particles now rather than just 1, right? So if your molality was 0.75, it is now 1.5. Right now, substitute the known values and solve that equation. So TB, it's 0.512 Celsius divided by the molality times, but times 150 molal, so equals. So basically, There it is. It's 0.768. So for every amount, for that amount of solute that you add to this solution, you're going to end up lowering the boiling point. No, sorry, this one is increasing the boiling point. Yeah, boiling point increases when you add stuff like salt into the water when you're cooking your pasta, but you would have to add way too much salt for that to actually affect it that much. So we don't add enough to do that. But let's say that's what you were doing, then it would increase the boiling point. So it would take longer for it to boil because it needs more time to reach that temperature. And then you substitute the values on there and you've got your answer, which is 2.79. So that's how much it would go up. And if the solution was 100, right, which is the boiling point of water, then you add that 768 and you get that. With freezing point is the same thing, except you're doing it, it's called depression. So you subtract. So if your answer gave you 2.79, then you subtract 2.79 from 0, which is the freezing point, and you get negative 2.79. See, that's what I was telling you. That is the freezing point of water. So when you added that salt, you would have had that depression happening. Okay, so there's a couple of problems on there. I did not include these on there, but you can practice them right now. I did not put any in the, I don't think I did any in the second assignment that I put up. So if you want to practice those, you notice it says 1.3 molal solution of calcium chloride in CaCl2, right? Because calcium chloride is CaCl2. So that means the molality would triple because you would have 1 molal of calcium, but 2 molals of chloride ions. And that makes it 3 total. So when you do that, you have to think about how many ions it's going to make. So you would have 1.34 molar times 3, which is going to give you 4.02 molal. Okay. All right. So now that you have that, the next thing that you would need would be your freezing point, your constant, right? Your constant. Now that constant you have to look for, and let me see, that would be KB of KB, that is a constant for okay. Hold on. Yeah, here is 0.512 Celsius per mole. Okay, and we do not have that for calcium chloride. Let me see, what is your KB for calcium chloride? Let's see if I can find it. Where are you? I think I've lost my spot. KB. All right, KB, where are you? Oh, KB, where are you? I do not see it on my stuff here. Okay, I guess it is the same 0.512 Celsius per mole, right? So we will say 0.512 degrees Celsius per mole. So over M times 4.02 M. Okay, so that would give us an answer, right? Let's see, 0.512 times 4.02 is going to give us 2.0506 Celsius per mole. So no, the increase, right? Wait, was it increase? Yeah, boiling. So in this case, the boiling is going to be 102.6. Let me see if that's what my answer is, because I do believe that's correct. But if not, then we have to look for the constant. I think the constant is a constant already. Like we don't have to look for another constant, but maybe we do. So that's why I'm gonna check right now. If we do, then there should be a constant given to you. Which I'm not sure that there is. I had it right. I don't have. Okay, here we go. 15. So 0.2 potential. Hey, yes, I got 102.06. Oh, sorry, 0.06. Yes, because it's 2.06, not 2.6. Yeah, that is correct. So it is the same number for everybody. Right, so to depress it, right, that is the other number, which is 1.86 lower. So the answer is 1.86 Celsius over molal, right, per molal. And that is going to give us 4 times 4.02 again, because we do our dissociating. And that is going to give us 1.86 times 4.02 is equal to 7.46 is what I get. Celsius. And the freezing point is 0, so that would be negative 7.46. And let me see, that's what I got. If that is, then that is correct. Yeah, 47. Actually, they say 48. I got, oh, sorry. I'm wrong. It is 48. I was not looking at the right number. Yeah, it's 48. 7.48. So that would be the negative. So if you added calcium chloride to water, it would be better than if you added sodium chloride, because it depresses it even more than salt. But salt is cheaper. That's why they use that. Okay. Now the next one of a non-electrolyte. Okay, so if it's a non-electrolyte, right? What is the answer? However much that molarity is, that's what it's going to be. So it says calculate the molality of a water solution of a non-electrolyte, given that the freezing point depression is 4.33. So if you have a 4.33, so that means it's negative, right? We need to go backwards with it. So molality would be, since it is a non-electrolyte, we will say that will divide that by 1.86. I would guess. Let's see, 4.03, 4.02 times 1. 4.33. 4.33. And that gives me 39. Where are you? No, that's not what I got. Okay, hold on. So it's the opposite. It's 1.86 divided by 4.33. No. But if it is a non-electrolyte, oh, I missed. Oh, I didn't miss anything. The molality is 2.33. Yes. Okay. So that's what I got. 2.33 molal. That's what it is. You multiply it times the factor, which is 1.86. So the negative 4.33 multiplied times that, which is negative, but you only know it's negative because it's a depression. And then you get the answer is going to be 2.33 molal. And that's it. All right. Now there is no more on this. And that is all we have. So you all have a great rest of your day, and I will, oh, actually, no, I won't see you until Tuesday. I will see you Tuesday. All right, take care. Bye-bye.